First of all, I'd like to congratulate on the great success of Yang-Mills gauge theory in describing the fundamental laws of physics. Due to the major advancement during the last 6 years, both in theoretical and experimental high-energy physics, it's now firmly established that the basic forces of nature are given by the non-event gauge theories, with SU3 gauge symmetry for strong interactions, SU2 times U1 symmetry for weak and electromagnetic interactions. And it's quite impressive that 3 out of 4 fundamental forces of nature are explained in terms of Yang-Mills theory. I still remember reading the original paper by Professor Yan and Mills when I was a graduate student. And there was a passage where they argued about the system of protons and neutrons considered as an isodoublet of particles. Yan and Mills argued if a proton is identified as an isospin, say, up state at a particular space-time point in the world, and if this fixes the identification of proton being spin up at everywhere else in the world, it will be in contradiction with the spirit of relativity. So if we want to avoid this phenomenon, we have to allow the freedom of independent isospin rotations at different points of space-time. And well, this idea had some appeal to me, so I still remember reading this passage. And so this is the beginning of the local gauge principle, which is reminiscent of general relativity theory and was the starting point of Yang-Mills gauge theory. It turned out that in order to realize invariance under local internal symmetry rotations, one has to introduce as many gauge fields, i mu n, as the number of parameters of the symmetry group. Then the beauty of the gauge theory is the fact that the symmetry becomes completely fixed once its symmetry group G is fixed and the representation of the matter field under G is chosen. So in the following talk, I tried to study mechanisms of generating non-abelian gauge symmetries within the context of string theory. So string theory is a kind of larger framework as compared to the ordinary quantum field theory. So it sort of embraces a different quantum field theory within a single string theory. So in some case, one can switch from one Yang-Mills theory to the other. So in ordinary field theory context, gauge symmetry is given and fixed. However, non-string theory is able to change non-perturbatively its local gauge symmetry. And most of the time, people try to use this mechanism to enhance the gauge symmetry. So this is called as a symmetry enhancement phenomenon. So I'm going to describe just 2 examples. One example is the example of the parallel branes, which is extremely elementary, and probably everybody in this room is familiar with that. And the second example is the symmetry enhancement coming from the space-time singularity. And this is probably a bit more mysterious, and we still don't understand quite a bit about this situation, so it'll be interesting in the future. So here I present the discussions in order to think again about the origin of the local gauge principle, in particular its possible relation to the certain types of space-time singularities. So let me start from the case of parallel D branes. So we know string theory is defined in 10-dimensional space-time. The ground state of string theory lives in gives the 10D supergravity theory. A ground state of open string gives the supersymmetric theory in 10 dimensions. On the other hand, when one considers the open strings with ends fixed to the DP brane, motion of the open string is confined to a p+1 dimensional hypersurface. The ground state describes a p+1 dimensional supersymmetric theory. So this is the situation. So here we have a DP brane extended spatially in p dimensions and p plus 1 dimension in space-time. And I have drawn just one open string attached to this D brane. So by definition, D brane, the endpoint of the strings cannot move in the perpendicular direction to the D brane. It is allowed only to move within the parallel direction to the D brane. So I have two endpoints, and these two endpoints are fixed to. So it cannot move out of this D brane. So its movement is confined to within this p plus 1 dimensional hypersurface. So what is this? Because the string has its own tension, this system shrinks. Eventually it shrinks so that the both endpoints are coming very close together. Then when this system is seen from far away, it looks like this is just a particle. And it turns out all the quantum numbers are adjusted so that this is a vector particle. And in the end, so we have a gauge field, massless vector particle, bound, but it's bound on this p plus 1 dimensional hypersurface. So one D brane gives one U1 symmetry. So in the case of two D branes, which are sort of close together, then there is one type of gauge fields with two endpoints attached to one to this D brane. Then there's another kind of gauge field which is attached to this D brane. So we have two different kinds of gauge fields. So they are, because they are attached to different D branes, so they are considered as a different particle. So two gauge fields. So there's U1 to the squared symmetry. But there's another type of open strings with now endpoints on different D branes. This D brane and this another D brane. And this is still a different type of gauge. So out of this, we also obtain a gauge field, because in the limit of these two D branes coming together, the length of this open strings goes to 0. Then this is again looks like a vector particle, massless. So this also gives rise to another gauge field. And if we consider open strings which has orientation, then there are two of these. So together we have 1, 2, 3, 4 different types of gauge field in this situation. Yes. So the symmetry is now enhanced to U2. So the non-double impaired part of U2 gauge symmetry comes from open strings connecting different type of D branes. So we can repeat this kind of construction for any number of branes, n branes, for which are on top of each other. Eventually, UN gauge symmetry is generated. So n parallel D branes gives rise to UN symmetry, and it's been found by Witten some time ago. When branes are separated from each other, the open strings stretched between them become massive vector fields, become heavy. And it turns out that this corresponds to exactly to the Higgs mechanism, breaking UN symmetry to its various subgroups. So when branes are really collapsed and sitting on top of each other, we have highest unbroken symmetry, UN symmetry. And if branes are far apart, even vector fields becomes mass, and it corresponds to exactly to the ordinary Higgs mechanism in standard field theory. So this is the situation of the parallel D branes. So there's another example of such symmetry enhancement, and that is the resolution of singularities. There is special type of singularities. We consider special type of singularities, say, in flat 4-dimensional space or complex 2-dimensional space, C2. And then we can sort of smooth this singularity. Given the singularity, we can resolve it or blow up and make it smooth. And the process of smoothing the singularity enhances the gauge symmetry of the system. And this is the second type of gauge enhancement mechanism. So I'm going to explain a little bit about it. Maybe I don't have time to go into the details. So the type of singularity is the so-called orbital type singularities. So we consider complex 2 dimensions, flat complex 2 dimensions, or real 4 dimensions, and divide by a certain discrete subgroup of SU2. So complex 2 dimension has a coordinate Z1 and Z2. Then we consider a transformation Z1, Z2, say going to minus Z1, minus Z2. And this is a case when gamma is the group Z2. Okay? Then we just identify Z1, Z2, and the point minus Z1, minus Z2. So we divide by this identification. In the case when gamma is equal to Zn, n is 2, 3, 4, ... Then Z1 coordinate Z1, Z2 goes with the phase e to the 2 pi in and e to the minus 2 pi in, and we identify these 2 points. Then in both cases, the origin Z1 is equal to Z2 is equal to 0 is fixed under this transformation and becomes a singular point. If a point is if a point under the application of the group transformation goes to a different point, then we can just take one of them and throw the other one away, and we can divide the system. But if it's a fixed point, we cannot divide by 2 or n the fixed point. So a fixed point becomes a singular point. So in the case of gamma is equal to Z2, it is called the A1 type singularity. As it turns out, the A1 singularity can be resolved, can be made smooth by blowing it up. Originally, this is a singular point, but we can convert it into S2, 2-dimensional sphere. Then we bring in a D-brane, and D-brane wraps around the S2, and then this becomes SU2 gauge group. In the case of gamma is equal to Zn, we have an AN1 type singularity, which can be made smooth by creating a chain of n-1 spheres and wrapping D-branes around these spheres to produce an SUN gauge theory. Actually, it's not difficult to describe the resolved, smoothed out A1 type singularity by making use of the explicit metric. This is based on all the work of ours. So, well, let me just, I think I don't have time to explain in detail, but just let me tell you the metric. So this is a solution to Einstein equation with the self-dual curvature. And A is a parameter. If you set A is equal to 0, this sigma x, sigma y, sigma z are these angles. So sigma x squared plus sigma y squared is just element of S2. Sigma x squared, sigma y squared, sigma z squared is a line element squared of S3. So when A is equal to 0, it looks like this is just a half flat space, metric on the flat space. And A is the deformation parameter. So, but it turns out when A is exactly 0, this space has a singularity at the origin, as is equal to 0. When A is non-zero, the possible singular point moves from R is equal to 0 to R is equal to A. But if you study the metric when R is close to A, then we find that the singularity is now, the metric is now written this way. So we have our S2 here, sigma x squared plus sigma y squared is just the length squared of two surface. So R is equal to A, so we have this part. And this part looks complicated, but under a simple transformation, R is close square root of R small r minus A is converted into this form. Then these first two terms are just the flat space in R2 or two-dimensional disk near the origin if psi has a period of 2 pi. So the original singularity is erased, you see, and we have our S2 of size A with radius A. So this is the process of blowing up or singularity smoothing. And so this sphere has a radius A, which is an arbitrary parameter. And when A goes to 0, the S2 vanishes. So from that sense, it is called the vanishing cycle. So, so in this case, we have just one vanishing cycle. And it turns out the vanishing cycles are homomorphic. So D-branes are able to wrap around them. So we have S2, which goes to 0 in A is equal to 0 limit. Then we take a D-brane, D2 brane, and wrap around it. And when this object seen from distance looks like a particle. And it turns out that this complex has a spin 1, as it turns out. So spin 1 particle, and the limit, and the mass of this object vanishes, because the mass of this object is the product of the D-brane tension times the surface area. When the size vanishes, the area vanishes, so the mass vanishes. So this is like a double boson for A non-zero, but in A is equal to 0 limit, it becomes the massless SU2 gauge field. Then we have a D-brane, which is sort of upside down, the inverted orientation. So that gives the opposite, the complex conjugate of double boson. So this gives the two pieces of SU2 gauge theory, A mu of say plus and A mu of minus. And actually in type 2 string theory, originally there is an abelian gauge field S3, and these three fit together to form SU2 multiplet. So in this way, starting from a singularity, by blowing up, we can generate the new gauge fields and new gauge symmetry, local gauge symmetry. In the case of SUN, the situation is a bit more complicated. So in order to resolve completely the singularity, we have to keep blowing up the surfaces. So create n S2 spheres, and then we wrap around each sphere by D-branes and generate, in the end, n squared minus 1, n squared minus 1 gauge field. So the system generates SUN gauge symmetry in the end. So resolved AN type singularity gives SUN gauge symmetry. So we see there is some interesting correspondence. Z2 creates SU2 gauge theory. Zn singularity gives rise to SUN gauge theory. And actually there's something which is called Mackay correspondence mathematics. We have different types of discrete subgroups of SU2. So we consider Z2 subgroup and Zn subgroup. And these are the series of cyclic groups of SU2. And there's another series of discrete subgroups of SU2 is dihedral groups, Dn. And there are three others, tetrahedron group, octahedron group, icosahedron group. Okay? These are all the discrete subgroups of SU2. And there is this mathematical observation by Mackay is that somehow the cyclic groups Cn has to do with SUN. Dihedral groups has to do with Dn, D-type Lie groups. And tetrahedron group, octahedron group, icosahedron group are tied with E6, E7, and E8. So altogether, these are the so-called ADE type gauge symmetry. And eventually, so by blowing up the singularities of these SU2, discrete groups of SU2, we can construct ADE type gauge theory. So there's some curious and mysterious connection between special types of singularities in spacetime. These days, I think these things are called codimension 2 singularities. And well, sometimes wrapping by the d-branes a singular object, we may generate spin, not spin 1, but spin 0 particles. And this is possible. And in this case, why you have generate the spin 1 particle is much like in 4-dimensional N=4 supersymmetry and mu theory, the monopoles have spin 1. N=4 supersymmetry and mu theory 4 dimensions, the monopoles have spin 0. And that is the difference. And in this system, there is enough supersymmetry in such a way that the object which is created it has a spin 1 part, is a spin 1 particle. So we are creating the locus gauge symmetry. Actually, there are many things which is still not quite clearly understood about this the symmetry enhancement coming from space-time singularities, and I think it needs further investigation. So thank you very much.